All right, how's it going? Welcome back to another video here in the series on group theory. We are on this new section now called matrix groups. And the last video was the first video in this new section where we introduced the general linear group. And if you remember, the general linear group was simply the set of all n by n invertible matrices. Or really just all invertible matrices. The fact that they're invertible implies that they're square matrices, right? But the only requirement on those matrices was that they were invertible. And we needed invertibility just so we could satisfy the inverse axiom of a group. But it turns out that you could have interesting subgroups of the general linear group where you're looking at sets of matrices that are not only invertible, but they are invertible and they satisfy additional constraints. And for certain types of constraints, you're going to get a set of matrices that have very interesting and useful applications, not just for math, but for other areas outside of math as well. And that's what we're going to be looking at in this video. There's going to be a certain group, which you might be able to tell by the name of the video. It's called the orthogonal group. And the orthogonal group is going to consist of the set of orthogonal matrices. So what we're going to be doing in this video is three main things. First, we're going to lay out what is an orthogonal matrix. Second, we're going to show that the set of orthogonal matrices do in fact form a group. And then finally, we're going to look at some applications of orthogonal matrices, but also special orthogonal matrices, and to see why we actually care about these things in the first place. So hopefully that makes sense. Now, to start off, if we're unfamiliar with what an orthogonal matrix is, we might be thinking, well, I've heard the term orthogonal before, but I've heard the term orthogonal in the context of vectors. But I haven't quite heard the term orthogonal in the context of matrices. So I want to introduce orthogonal matrices by introducing orthogonality in the context of vectors. So hopefully we know what a vector is. A vector is an element of a vector space. It's a thing that can get added and scaled. But conceptually, we can think of a vector we can visually think of a vector simply as an arrow in space. And it might look something like this. We'll give it a name. We'll call it A. So this could be a way to visually represent a vector. We could draw another vector, and maybe we can call that guy B. And one of the initial questions that people often ask when looking at maybe two vectors is, are these vectors perpendicular to each other? In other words, do the angle that they form here, is this angle 90 degrees or pi over 2 radians or whatever? Right? And just by looking at this set of vectors, it looks like these are slightly less than 90 degrees. I didn't draw them exactly at 90. But one way that you could check to see if two vectors are perpendicular to each other is by computing what's called their dot product. Right? And their dot product is denoted like this. There's a dot in between the two vectors, A dot B. And there is an algebraic way of calculating it and also a geometric way of calculating it. But it's the magnitude or the length of A times the magnitude of B times the cosine of the angle between them. So rather than putting 90 with a question mark, I'll put theta as the angle between them. So this is the dot product for two vectors. And if the dot product ends up equaling 0, I don't want to say it's always 0, but if it equals 0, then it turns out that the two vectors happen to be perpendicular to each other. And then this is kind of like the baseline test to determine that they're perpendicular. Reason why, too, is because if you plugged in 90 degrees in for cosine of theta, or in for theta, then you're going to get cosine of 90 or just 0, and that's why the whole thing goes to 0. Right? So showing that two vectors are perpendicular by showing that their dot product is 0 is kind of like the starting point. But it turns out that the dot product has a general type of structure And the general underlying structure behind a dot product is the fact that it is bilinear. It is linear in both of its arguments. So what we could say is that this guy, little dot, is actually just one instance of something more general, something that could be called a bilinear form. I'm going to write this, a bilinear form. Oftentimes in linear algebra, we're interested in symmetric positive definite bilinear forms, and those are called inner products, in case any of those terms sound familiar. But the main idea is that the dot product is just one instance of a bilinear form. And it turns out that because it's just one example of a bilinear form, you could come up with other types of bilinear forms other than the dot product. Maybe let me just call a general bilinear form B, uppercase B for bilinear. And maybe I want to have some general type of bilinear form B which takes in our two vectors, and maybe its output would be 0. And it turns out that if the general output, if the output of a general bilinear form acting on two vectors, if that output is 0, then what we do is we say that the two vectors are orthogonal to each other. So orthogonal gets introduced in the context of vectors as a generalization of being perpendicular. We say that two vectors are perpendicular if their dot product is 0, but more generally if their inner product is 0, or if a bilinear form acting on these two vectors is 0, we say that the two vectors are orthogonal. So that is kind of the more technical way of introducing what it means to be orthogonal, but conceptually in our heads we should just think of orthogonal as perpendicular. At least that's how I visualize orthogonality. If I hear that two vectors are orthogonal, I think that they're perpendicular to each other. Okay. So some of that may or may not sound familiar to you, but that's where the term usually gets introduced in math, just talking about vectors being orthogonal. But then the question comes up, how is a matrix orthogonal, right? If orthogonality kind of is a generalization of what it means to be perpendicular, how do you have perpendicular matrices to each other, right? And that's going to take a little bit of work to see, and what we're going to do is we're going to write out the definition for what it means to be an orthogonal matrix, and then we'll really be able to unpack that. But before we do that, I just want to introduce one more concept in case we haven't heard of it, which is called orthonormality. So two vectors are going to be orthogonal if their dot product is 0. So let me even just write this. So let's write A and B are orthogonal if their dot product or inner product or whatever bilinear form is acting on them is 0. We add kind of a suffix, so not just orthogonal, but orthonormal if we place a further constraint on these two vectors A and B. Specifically, if A and B both have a magnitude of 1, then we'd say that A and B are a set of orthonormal vectors. It's kind of like their length is normalized. The way that we could see this, or at least that we could define this conceptually, is that if A and B are orthonormal, their dot product is 0. A dot B is 0. But now let's take the dot product between A dot A and B dot B. If A and B are orthonormal, they both have a magnitude of 1. So let's just plug in what these dot products are into this geometric definition right here for the dot product. So I'm going to have A dot A is going to be the magnitude of A times the magnitude of A again, times the cosine of the angle between them. But the angle between any vector and itself is just 0, so the cosine is 0. If I said that A had a magnitude of 1, this is going to be 1, this is going to be 1, and this is going to be 1. So it's 1 times 1 times 1, or just 1. And the same thing for B. So if two vectors are perpendicular and they both have a length or magnitude of 1, we say they are orthogonal. And we could generalize this not just to 2 vectors, but to a set of n vectors. Maybe if I had a set of n vectors, v1, v2, all the way through vn, then each of these vectors are going to be orthonormal with each other if the following condition is satisfied. If I were to take the dot product between any two vectors in my orthonormal set, then the dot product is going to be 0 if I is not equal to j. Meaning if I take the dot product between v1 and v2, v1 and v3, v1 and vn, v2 and v7, whatever, as long as they're different vectors, they should be perpendicular to each other, or hence orthogonal to each other, so their dot product is 0. But in the case where I equals j, I'm taking the dot product of a vector with itself. So in the case where I equals j, then I'm going to get 1 right here. And this condition right here is really what the general way of saying that a set of n vectors is orthonormal. Now still, that's not getting to the question of, well, how does that relate to matrices? How do we have orthogonal matrices? We're just talking about orthogonal vectors and then orthonormal vectors up here. Well, this is going to be kind of the background needed to understand what an orthogonal matrix is. So hopefully these ideas make sense. Now, what I'm going to do is I'm going to write out the definition for an orthogonal matrix, and we're going to start to piece together how the definition of that matrix relates to the idea of specifically orthonormal vectors. Okay, so now we have the definition here for an orthogonal matrix, as opposed to a set of vectors that are orthogonal. So let's go through it together. It says that a real n by n matrix is considered an orthogonal matrix if this condition right here is satisfied. And the matrix that we're going to look at is denoted as A. So if we take A times A transpose, or if we take A transpose times A, we get back to the identity matrix. Okay. Now, what you could do, and what I did when I was first learning linear algebra, is I remember I needed to have this idea in my head that orthogonal matrices were these types of matrices right here. And I tried to memorize this condition. There's actually another condition that I tried to memorize that can immediately follow up from this. Maybe let's go through that right now. So we automatically know that a matrix times its inverse, or the inverse times the matrix itself, gives us I. That has to be true for any invertible matrix, right? But orthogonal matrices have the property where the transpose is equal to the inverse. So one way of describing the conditions required for an orthogonal matrix is this right here. Another, maybe more compact condition is that the transpose of that matrix needs to be the same as its inverse. These are both equivalent. And what I ended up doing in my intro linear algebra class is like the night before some quiz or some test or whatever, you're trying to remember, oh, the orthogonal matrix is where the transpose is the inverse condition. And it's just not a good way of really understanding what an orthogonal matrix is. It's not incorrect, like this, that is what the definition is, but you don't gain an intuitive understanding of what's going on. And that's what I hope to achieve here, to write out the definition, but also to gain an intuition for what's going on. Okay. So let's try to do that here. And what I'm going to do is I'm going to work specifically with this condition right here. A transpose times A gives us I. So let's start by defining A. And it says that A needs to be a real n by n matrix. So what I can do is I can construct this matrix as a series of n different columns. And maybe I can call my first column V1. And notice that I'm using vector notation. My second column I can call V2. And this can continue all the way through my nth column, V sub n. We can represent each column as an n-dimensional vector. And if we have n of those n-dimensional vectors, then we have an n by n matrix right here. Okay. So this is how we can construct just an n by n matrix A as a set of n by n vectors who are the columns of that matrix. Now, to see how orthogonality plays into this, let's end up looking at the equation A transpose A equals I. We know that if we were to transpose a matrix, we are interchanging the rows with the columns. So another way of writing A transpose out in this notation right here is, rather than calling the first column V1, we're going to call the first row V1. So now V1 becomes the first row in A transpose, V2 becomes the second row in A transpose, and this continues all the way through Vn as the nth row in A transpose. So this is A transpose. Then we still have A, which we're just going to write out like this. So we're going to have V1, V2, all the way through V sub n, like this. And we know that based off of the condition right here, that this product of A transpose times A needs to give us the identity matrix. Where again, the identity matrix is a matrix that has the number 1 on the main diagonal, and it has zeros everywhere else. Okay. So this is how we can express the condition for being orthogonal. And I want us to just take a minute to think about how matrix multiplication works, right? If we were to take, here, let's write this out. Let's say this guy is A transpose, this guy is A, and maybe we already said that the product is the identity matrix I, but let's for a second just say that it's going to be some matrix that maybe we don't know what it is yet, and we're going to call that matrix M. And we can construct the elements of M by thinking about matrix multiplication. So how do we construct the ijth element of M? How do we construct, let's see, I'm not quite sure where to stand. How do we construct M sub ij, or the element that's in the ith row in the jth column of our matrix M? Well, what we end up doing is we take the ith row from here and perform a dot product with the jth column of here. Right? That's kind of the way that we learn how to perform matrix multiplication. So let's just ask ourselves, what is the ith row in our first matrix? Well, if the first row is V1, the second row is V2, third is V3, then the ith row is V sub I. Right? And then we perform a dot product with V sub I on this second input right here, which would be the jth column of our second matrix. And then we just ask ourselves, okay, what is the jth column of this matrix? Well, if the first column is V sub 1, second is V sub 2, third is V sub 3, the jth column is going to be V sub j. So in general, that is how we can compute elements of the resulting matrix after the product, right? So we say, okay, if this makes sense, that this is how we can compute elements of our resulting matrix, let's just now see what is our resulting matrix. Well, it's the identity matrix, right? And the identity matrix has a very specific structure, where it's going to have ones on the main diagonal. In other words, where the row index is the same as the column index, and it's going to have zeros off the main diagonal when the row index is different than the column index. So let's write that out mathematically. We know that this is how we can obtain elements of the identity matrix, or just any matrix product, right? And now for the identity matrix, we're going to get ones on the main diagonal when the row index I is equal to the column index j. And we're going to get zeros everywhere else whenever the row index I is not equal to the column index j. And hopefully this, put a box around it, hopefully that condition looks familiar, right? That is the condition that in the previous whiteboard, this was the condition in order for these vectors to be orthonormal. Okay? So this is where we make the connection between a set of orthonormal vectors and orthogonal matrices. The intuitive way of thinking of an orthogonal matrix is that it is a matrix A, like this, whose columns are a set of orthonormal vectors. Now, I'm not making a verbal typo when I say that, and this can be a little bit confusing, but the columns here are specifically orthonormal, although the matrix is called orthogonal. It's not called an orthonormal matrix, it's an orthogonal matrix, despite the fact that the columns are not just orthogonal, they are orthonormal. If the columns were purely orthogonal, then they would be 0 whenever I is not equal to j, because they'd all be perpendicular to each other, or quote unquote perpendicular to each other. But they might not be normalized. They might not all have a length of 1. So then a matrix that has just a set of a matrix that has a set of orthogonal vectors as its columns would produce a diagonal, some general diagonal matrix when we compute A transpose A. But in the case where the columns of our matrix are not just orthogonal, but they're orthonormal, then when we compute A transpose A, not only do we have zeros everywhere else, but because the lengths of our vectors are 1, we have 1s along the main diagonal, and hence we get the identity matrix. Okay. So maybe let me write that. I'm saying words, but let me write that. An orthogonal matrix, we can also write as a matrix whose columns are a set of orthonormal vectors. Orthonormal vectors. Okay. And this is how we can make the connection. This is why we call the matrix orthogonal. To be honest, the natural question is, well, if the columns are orthonormal, why don't we call it an orthonormal matrix? I'll be honest, I don't know the answer to that question. It's a good question. Maybe I probably should have looked it up, but somebody I'd recommend maybe look it up and see why are these things called orthogonal and not orthonormal matrices. But regardless, this is the connection that we can make between how we typically think of the phrase orthogonal or orthonormal in terms of vectors and how we can connect that to the word orthogonal in the phrase orthogonal matrix. So hopefully that makes sense. That's why we call these things what they are, and why we don't typically just memorize the transpose equals the inverse condition blindly. Right. Now, one more thing that I want to mention about orthogonal matrices before we move on to showing that these things actually form a group is that hopefully we're familiar with the properties of determinants, which we should be from at some video, which is that the determinant of a product of matrices A times B, is the same as the product of the individual determinants by themselves. Determinant of A times the determinant of B. Right. Now, what we can do is to apply this condition right here to look at what the properties for the determinant of an orthogonal matrix must satisfy. So we know that if this condition right here is true, A transpose times A gives us the identity. Let's just plug in A transpose times A and the identity. So let me do this here. So we know that A transpose times A gives us the identity. If we were to take the determinant of both sides, then we're going to get the determinant of A transpose A equals the determinant of the identity. After all, these are just the same matrices, right? We know that the determinant of the identity is just the number 1. And from properties of determinants, we can break this into the product of the determinant of A transpose times the determinant of A. Right? So hopefully that makes sense. But we also know, hopefully, from properties of determinants, that the determinant of A transpose it has to equal the determinant of A. And this is not just true for orthogonal matrices. This is true for any matrix. That if you had a matrix, you were to take its transpose, then the value of this will always equal the value of this. So rather than writing out the determinant of A and the determinant of A transpose, since I know that these values need to be equal to each other, then I'm just going to write the determinant of A squared, because this is the same as this. So now I have that the determinant squared of A gives me 1. And then we ask ourselves, how can the square of something produce the number 1? Well, the only way that's possible is when the determinant is equal to +1 or -1. So this implies that the determinant of A equals plus or minus 1. And again, let's remind ourselves where that came from. That came from all of that, or this right here, started with the condition that A transpose A equals I. So the overall statement that we're trying to make here is that this is what orthogonal matrices are, but an additional property of orthogonal matrices is that their determinant, if you were to take the determinant of an orthogonal matrix, it will either be +1 or -1, one of those two values. And that's a lot different than in the general linear group case, right? If you remember, we went through a claim in the general linear group case where we said that we could define the determinant on GLN of F to the field excluding the 0 element. And we said that the determinant was a surjective group homomorphism. It turns out you could go through the exact same logic to show that you could replace the general linear group with what we're going to define as the orthogonal group. And rather than writing some general field here, we're simply going to write the set of the numbers plus or minus 1. So this set gets compactified down to a set of only 2 elements. So that's something else that I want to make clear with orthogonal matrices. This property will be true for any orthogonal matrix. And I was about to say we're going to move on, but one more thing that I want to make clear in case it's not. Something we haven't focused on too much on this board is kind of the very beginning part of it right here. We know for a matrix to be invertible, it needs to be square, so it needs to be an n by n matrix. But we also said that this is a real n by n matrix. And I want to make something clear here with that. In the previous video, we said that the general linear group can be defined on an arbitrary field, but we can typically think of that field as a set of real numbers or complex numbers, just as a starting point, even though it works for a general field, right? However, for orthogonal matrices, we're not saying that it is a real matrix, and it turns out that we're just thinking of the set of real numbers as one example of a field. It turns out that in order to have an orthogonal matrix, you need to have a matrix that is real. This is no longer just like you can think about it this way. No, the elements of an orthogonal matrix have to be real. Okay, so that's an additional restriction. So you cannot have a complex orthogonal matrix. Okay. It turns out that you could have a matrix that satisfies a similar type of condition where the transpose complex conjugate is equal to the inverse. Basically, rather than filling up a matrix with real numbers, you could fill those up with complex numbers, but then you wouldn't have an orthogonal matrix. You would have something that is called a unitary matrix. It's a slight generalization of the orthogonal matrix. So that's the last point that I want to make, is that orthogonal matrices have to have real valued elements. It's no longer an option to have just elements from a general field like what we did in the last video. Now I'm done talking about just orthogonal matrices, right? Let's show that these things actually form a group, which is the whole reason why we are talking about these things in a video series on group theory, right? So I'm going to erase the board, and then we're going to define the orthogonal group and go through that together. Okay, so now we have arrived at the orthogonal group. And here's the definition. So it says that the orthogonal group O of n, that's the notation used to describe the orthogonal group, is the set of matrices in GLN of R. So notice that it's no longer GLN of F, but specifically GLN of R, such that that matrix is an orthogonal matrix, right? This is just the condition, again, to be orthogonal. So it says, okay, it turns out that there is this set of orthogonal matrices, and we're going to conveniently call it the orthogonal group. So we should probably show that this set is, in fact, an orthogonal group where the binary operation is just the standard matrix multiplication. So in order to show that, we already see that the orthogonal group is the set of matrices in GLN of R. But the set of matrices in GLN of R that satisfy a certain property. So that immediately tells us that at least we know that O of n, the orthogonal group, is a subset of GLN of R, right? So if we want to show that not just is this a subset, but is also a subgroup, there are two criteria that we could show that, or two criteria we could use to show that this is in fact a subgroup of GLN of R. The first is we want to show that O of n is non-empty. So maybe let's just go through that real quick. Well, actually, let me just mention these real quick. So the first is that it's non-empty, and the second is that if we have two matrices in this subset, so if we have O and B, or A and B in O of n, then that implies that the quantity AB inverse is also in O of n. Okay. So this is what we're going to have to show. And if we can satisfy these two requirements, then O of n is a subgroup of GLN of R. So first one, we want to just show that it's non-empty, that there is some matrix that belongs in this set in the first place. And you can come up with a bunch of different examples, but probably the most obvious one is just the identity matrix. All we need is some matrix in GLN of R. We know the identities in GLN of R because it's a group, so it has to have the identity. And then we ask ourselves, if we replace the identity with A in this equation, is the equation true? And the identity transpose is the identity, times the identity gives us the identity, which is that. The identity makes everything really nice, right? So we know that for this first requirement, that the identity matrix is in, the identity matrix is in O of n. So that gets satisfied. Now just going on to this requirement right here. And this is just a matter of doing a little bit of algebra. So we know that A and B are in O of n, meaning that A transpose A gives us I, and then also B transpose B gives us I. And we want to show that A, B inverse, this product, is in O of n. So what we would need to do is show that this quantity, A, B inverse, if we took its transpose and multiplied it by just A, B inverse, we want to show that we do in fact get I. So let's just go about doing that. First of all, we know that if we take a transpose of a product, that is the same thing as inverting the order, so then having B inverse first and then A second, and then transposing each of those matrices individually. So B inverse transpose, A transpose A, B inverse like this. This is I. Now, because A is an element of the orthogonal group, we know that A transpose A gives us I. So this quantity right here is just the identity. And that effectively goes away in the matrix multiplication, leaving us with B inverse transpose B inverse equals I. But same thing, we know that B is an element of the orthogonal group. So if B is an element of the orthogonal group, then it will satisfy the property, not just this property right here, but the other one that we mentioned in the previous whiteboard, where the transpose of the matrix is equal to its inverse. So I'm just going to replace the inverse of B with the transpose of B. So now I get B transposed, that quantity gets transposed, times B transpose equals I. The transpose of A transpose is just the matrix itself, so this is the same thing as just B times B transpose. gives us I, and we know that's true because B is an element of the orthogonal group. Okay. So because both of these requirements right here are satisfied, therefore not only is the orthogonal group a subset of GLN of R, but it is a subgroup of GLN of R. Do that. Okay? So hopefully that makes sense. Now, I said that in the beginning of the video that we are not only going to look at the orthogonal group, but we're also going to look at the special orthogonal group. And same idea as what we were doing with the special linear group, SLN of F. The special orthogonal group is going to be the set of matrices in the orthogonal group that have a determinant of 1. Remember, that was kind of the condition. Whenever we said that we had the special something group, the term special refers to the matrices with a determinant of 1. So maybe let's just write that out real quick. I'll just erase this subgroup criteria because we just showed that. And then we'll introduce the special orthogonal group as well. And both the orthogonal group and the special orthogonal group are incredibly important when talking about physical applications, which is why I really want to write this out. So the special orthogonal group is called SO of N. And it is going to be the set of all matrices in the orthogonal group, so the set of A in the orthogonal group, with the property that their determinant is 1. We said that in the previous whiteboard, the determinant could either be +1 or -1. The set of matrices with the determinant of +1 are the matrices in the special orthogonal group. So just introducing these two, yeah, hopefully that makes sense. Now to finish off the video with the stuff that I'm really wanting to get to are the applications of this. How do we, not only how do we use these, but really what do these get used for? What do these matrices get used to represent? What we're going to do is to keep it simple and to keep the video not too long, I'm only going to look at the two-dimensional cases, so O2 and SO2. But note that these concepts are going to generalize to a higher number of dimensions as well. It's just easier to show when you keep the number of dimensions relatively small. So what I'm going to do is I'm going to erase the board, and then we're going to go through the first claim. At least I think we're going to start with SO2 and then see how does SO2 get used conceptually, or what is its usefulness when you apply this thing. Okay, so first, I think real interesting claim that we can start to make about both, well, in this case, the special orthogonal group and then eventually the orthogonal group. But let's start with this one. It says here that SO2 consists of all rotations of R2 around the origin. And I think the statement by itself doesn't do this claim justice. So it really helps to understand what this is actually saying before we can appreciate how important it is. So first of all, when they're saying all rotations of R2 around the origin, what you can imagine is if I were to draw kind of a visual representation of R2, aka an XY plane, so we can just call this guy R2. You can imagine that if you were to draw pretty much anything, that if you were to rotate it, here, let me start by just drawing something. I'll just draw an arrow to make this simple. Let's say that I'm working in R2 and then I have an arrow. And if I were to rotate this XY plane about the origin, you could imagine me almost taking a pin, putting it in the location of the origin, and then rotating space either clockwise or counterclockwise. And if we were to perform a counterclockwise rotation by theta degrees, then what I would be doing is I would be taking not only this arrow, but anything else in this two-dimensional space and rotating it in this general direction by theta degrees. And what this claim is telling us is that the group SO2, the special orthogonal group, is the group that consists of all matrices which represent all possible rotations of this form. Okay. So let's first go about proving that, and then think about what that means. So first of all, SO2 is going to be the set of all 2 by 2 matrices that are orthogonal, that have a determinant of 1, the special part, right? So let's say that we have a matrix A in SO2, and if A is in SO2, we can come up with its general structure like this. It's going to be some 2 by 2 matrix, right? Now, what we can do is we can say, well, if we know that it is an orthogonal matrix, it should satisfy some conditions. Specifically that A transpose A gives us the identity, and also that A transpose is the same as A inverse. So let's just start by computing both A transpose and A inverse if we know that this is what A is equal to. So if this is what A is, then if we were to transpose A, we're just going to interchange the rows with the columns. So now instead of the first row being AB, now the first column becomes AB, and the second column becomes CB. So that's A transpose. A inverse is going to be 1 over the determinant of A. And then if you remember, we interchange the elements on the main diagonal, so D and A get swapped. And then we flip the signs of the off diagonal elements, so that then we have minus B and minus C, like this. But then let's now remember what the special part of SO2 means. That means that the determinant of the matrix is 1. So even though we have this prefactor in front, 1 over the determinant of A, this is really just 1 over 1. So the matrix simplifies to just writing D, negative B, negative C, A, like this. So now we have an expression for both A transpose and an expression for A inverse. Because A is an orthogonal matrix, this expression, or this matrix right here, needs to equal this matrix right here. And what we're going to do is we're going to set them equal to each other to put constraints on what the possible elements for A, B, C, and D need to be. So let's just do that real quick. So on A transpose, I'll write that over here. That'll be my matrix on the left. I'm going to have A, C, B, D. And for my matrix on the right, I'm going to have A inverse, which is D, negative B, negative C, A. And if we were to compare these element by element, looking at the top left element, we see that A needs to equal D. And the bottom right element tells us the same thing, D equals A. So you can just reverse that, right? Then looking at the top right element, we get that C equals negative B, and the bottom left gives us B equals negative C. So what we end up getting is that the main diagonal elements have to be equal to each other, and the off diagonal elements need to be equal with the exception of a sign. So that tells us that we can simplify how we write out our original matrix A. It doesn't have to be this general A, B, C, D, but instead we could write it solely in terms of A's and B's, or any of the 2 variables. So we could have AB at the top, and instead of C, we know that C is the negative of B, so we can rewrite this as negative B. And we know that D has to be the same as A. So what we've just shown, purely from the conditions imposed by A being in SO2, is that any matrix in SO2 is guaranteed to have this form right here. Now, if we were to continue this and think about now computing the determinant of A, we know that the determinant of A is 1, but if we were to actually write out what its structure looks like in terms of A's and B's, here's what we would get. So if I were to write the determinant of A, that's the product of the main diagonal elements, which in this case is little a squared, minus the product of the off diagonal elements, which is minus negative b squared, or just plus b squared. Since it's an SO2, I know that its determinant needs to equal 1, so I get that the condition a squared plus b squared equals 1. And now all we have to do is we make a simple change of variables to see that any matrix in SO2 represents a 2-dimensional rotation. Hopefully this looks like some trigonometric identity we've seen before. Something squared plus something squared equals 1. So if I just conveniently replace, let's set A to be cosine theta, and B to be sine theta, now you can see that we get the standard trig identity, cosine squared plus sine squared equals 1. And when we make that substitution, now A doesn't just have the structure of A, B, negative B, A, but it can be expressed as cosine theta, sine theta, negative sine theta, cosine theta. Or you could rearrange variables in such a way where you have the minus sign right here as well, which is what Dexter ends up doing. He writes everything in terms of A's and C's, and then when you do that, you'll naturally get this. But the main idea is and what he's trying to show, and what we're trying to show here, is that any matrix A in SO2 will have this form of cosine theta, sine theta, negative sine theta, cosine theta. It will represent some rotation about two-dimensional space. Because after all, if we're familiar with how rotation matrices look, structure-wise, all rotation matrices, at least in 2 dimensions, will have this structure. They can be defined in terms of sines and cosines. So what this means, mathematically and for other areas, is that SO2 represents the group of all 2-dimensional rotations. That's for n equals 2. But you can imagine, and Dexter goes through this in his notes, that if you were to generalize this to SO3, that would represent some rotation in 3 dimensions. Now, in SO2, you kind of just can pin the point, being the origin, that you want to rotate around. However, in 3 dimensions, it's not like you can just pin an origin. Or I mean you can pin the origin, but the orientation in where you put the pin is going to differ. Basically, the way that this would generalize in 3 dimensions is that SO3 is the group of all rotations about some specific axis in 3 dimensions. And you can imagine how this will generalize higher, because we had just in general SON corresponds to rotations in n dimensions. So what this means is that if you want to model anything rotation-wise, if anything undergoes a rotation, I can only imagine the countless possibilities. There are obviously a bunch of them in physics. Whenever anything rotates in physics, I can also imagine in graphic design, if you want to imagine something rotating with whatever you're trying to create, the way that you can represent that and encode that with the matrix, you simply have to look at the elements of SO2. This is the mathematical way of representing rotations in space. It's such a general statement, but this is why we care about these things. A lot of things rotate, and it turns out they can all be represented by something in SON, depending on the dimensionality of the space that you're working in. Okay. So really cool ideas that this can represent the group of rotations. Especially too when we often think of group theory, it's the study of symmetries, right? And occasionally throughout this video series, we've been able to tie a group in with an associated symmetry. We were able to do that a lot with group actions, but I think this is a very clear visual picture as to what the physical transformation that's occurring when working with this group right here. Every group element corresponds to some rotation. That is about at least to me, as intuitive as of a visual picture as you could possibly get, right? So really, really important group, the special orthogonal group. And we've shown that at least in the case for 2 dimensions. Now, again, the video series, or this video is not titled the special orthogonal group, it is titled the orthogonal group. And the difference between the special orthogonal group and the orthogonal group is that the orthogonal group also has matrices which have a determinant of -1. So that's going to be what we talk about next, is to say, okay, well, how if we can think of SO2 as the group of all rotations in 2-dimensional space, how can we think of the group O2? It obviously needs to contain rotations for all of the matrices that have a positive determinant, but what about the matrices that have a negative determinant? So I'm going to erase the board, and then we're going to answer that question next. All right, now to finish off the video, we're going to look at this claim right here, which now looks at O2 as opposed to just SO2. It says that O2 consists of all rotations of R2 around the origin, which is the SO2 elements, or it can contain a reflection in a line passing through the origin. So that this part right here looks at the elements that are in O2 but not in SO2. Now, to see this, the proof I think is going to be a little bit hand waving in the sense. I more just want to get the conceptual idea across, and hopefully that will make sense. We'll see how this goes. We'll see. So first thing is, it's not going to be entirely hand wavy. I'll say that. So first thing is that we know that SO2 is the kernel of the determinant, where if we defined this is kind of similar to what we did in the last video, right? Where if we defined, if we defined the determinant as a function going from ON to plus or minus 1, we know that the kernel of the determinant is SON. Right? This the same logic would apply from when we were talking about the general linear group. Now, because and this is also a surjective group homomorphism. Now, because SON is a kernel of some homomorphism, that tells us that SON is a normal subgroup of ON. In other words, SON is a normal subgroup of ON. And because we have a normal subgroup, we can now apply the isomorphism theorem to this group and this subgroup. Specifically, what we can do is we can take ON and take the quotient group with that and a normal subgroup, being SON. And it's going to be isomorphic to the image of this function right here, the determinant, right? And the image is just a set of two elements. And we know that any group that has two elements has to be isomorphic to C2. So what this tells us is that the quotient group, ON divided by SON, is isomorphic to C2. Now let's just remind ourselves again what the quotient group is. The quotient group is the set of left cosets of SON and ON. So one of those, and if it's isomorphic to C2, it's going to have two elements. One of those elements needs to be the identity, right? And that's when we have, let's do this. We have the identity matrix E multiplying SON, right? In case what I'm doing is unclear here, I'm just writing out the structure of a general left coset. Elements of this quotient group are left cosets. So it's some element from ON multiplied on the left, and then we have the overall subgroup SON on the right. So what I'm writing out is a left coset. The identity matrix times anything in SON is just SON. So if we were to write out the two elements in this quotient group, let me do that over here. If we were to write out the two elements in ON over SON, one of those elements is just going to be SON by itself. SON by itself. There needs to be some other element, some other left coset in this quotient group, and the way that we can obtain that is just by coming up with a matrix here that is in ON but is not in SON. The way that we can do that is just induce a minus sign like this. The reason why is because we know that the determinant of this matrix right here is negative 1. 1 times negative 1 minus 0 times 0 is negative 1. And I mean, therefore it's not in SON, right? So whatever this element is, meaning like this matrix times any matrix in SON, that resulting quantity cannot be in SON, just because SON's closed. So that tells us something, that one left coset is SON by itself. The other left coset, because there's only two elements, right? The other left coset is going to be 1, 0, 0, negative 1 times some element of SON. And we could have come up, again, with any matrix right here to construct the left coset. There are different ways where we can write the same left coset. We don't need to use the same element. You could put negative 1, 0, 0, 1. That would represent the same left coset. But the idea is that there are one of two possible left cosets for this group. So hopefully that makes sense. We're applying the isomorphism theorem and writing out the elements of the quotient group ON divided by SON. And what we're going to do is we're going to see that, like how this claim is split into one of two possible cases, I want to show that each of these left cosets corresponds to one of the two options here. The first one is where they're saying that we're going to have all rotations of R2 around the origin. We've already shown that that would be, well, I guess SO2, right? I'm keeping it general in n dimensions, but SO2 would represent all rotations of R2 around the origin. So now what we just want to show is that the remaining elements, these guys right here, are going to correspond to some reflection in a line passing through the origin. So let's see if we can understand, and that's what the remainder of this is going to be. I want to explain why this quantity right here will correspond to a reflection passing through the origin. And the first key to doing that is just to understand how this matrix is going to act on a general vector. Not this left coset, but just this matrix by itself. So what we can do is let's say that we're working in, because this is a 2D grid, and I think what I should really be doing, let me change all these n's to 2's. Because after all, you can't have a 2 by 2 multiplying an n by n. Hopefully, you see what I was doing there, right? Like, the isomorphism theorem applies in the n by n case, but where this is the left coset, you want to have SO2, because you're multiplying by a 2 by 2. What I want to do right now is just to see how this matrix, 1, 0, 0, negative 1, acts on a general vector in R2. So what we can do is, let's say this is my vector, and it has a horizontal component of x and a vertical component of y. And I want to see what happens to this vector when I act it on, when this matrix acts on it. So now I have 1, 0, 0, negative 1 acting on this vector xy. Well, I know the output is going to be some other vector, where the top component is going to be 1 times x plus 0 times y, or just x. And the bottom component is going to be 0 times x plus negative 1 times y, or negative y. So what we see that is going on here, what this matrix is physically doing, is it's taking the bottom component and swapping the sign. We started with a positive y, and now we have a negative y. That's what it's doing mathematically. Let's see what it's doing visually. Maybe we can call this v, this vector v, before the transformation, and we'll call this vector v prime after the transformation. It started before the transformation as xy. Now after the transformation, it's x minus y. Minus y. This new vector here is v prime. So what I'm trying to get at is that what this matrix, the 1, 0, 0, negative 1 matrix, what it is physically doing is it is taking any vector and reflecting it about the x-axis. You can imagine that if you were to almost swap the orientation, kind of reflect it like this, anything that, it's like a mirror image, right? If it starts above this line, then it gets reflected to below this line. If we had another vector that started below the line, after the reflection it would go to above the line. So what this matrix is corresponding to is a reflection about this x-axis right here. If we were to swap the negative sign, where we had a negative here and a negative 1 here and a positive 1 here, that would just be the opposite. That would be a reflection about the y-axis. And you would see that by xy going to negative x positive y. Okay. But hopefully that makes sense. What this matrix is physically doing to all of the arrows, or all the vectors in the two-dimensional space. So if that makes sense, then we can just combine the pieces together. We first ask ourselves, what does SO2 do? And that performs a rotation about some axis, or a rotation by some angle theta, right? So what we can do, and let me erase some stuff so this is clear. I'm gonna erase let's just erase all this right here. Hopefully that makes sense. This is what I want to keep, the set of left cosets right here. And what I want to do is I want us to just think about what elements of this form, or what elements in this left coset do. Elements in this left coset are going to have the following structure. They're going to be 1, 0, 0, negative 1 times some matrix A, where A has to be an element of SO2. Right? And if you can imagine if we were to have this matrix, 1, 0, 0, negative 1, times some matrix in SO2, which I can just write generally as cosine theta, sine theta, minus sine theta, cosine theta, we just has shown that any matrix in SO2 can be represented like this. When that acts on a vector, let's think about what it does to that vector. When we first have this vector get applied, or when we first apply this matrix to an input vector, that will take, here, let's do this. That will take that vector and it will rotate it by some angle theta. Okay, so maybe let's put some names on this. We'll call this guy A and this guy B. So and then our vector V. Okay, so we got our names. After A acts on V, now maybe it's rotated up here. Right, so we started here, then it got rotated up by some angle theta, so now where it's here. And that would be the new vector in the current state up until this point. Then when we apply B to it, what that will do is that will reflect it, just like what we said, that will reflect it about the x-axis. So now, the new vector, instead of being like this, it's going to look like this. And this vector right here is B times A times V. Okay. So what you could imagine is if we started with a vector like this, and then we ended up with a vector like this, rather than thinking about them as two separate transformations, where we have a rotation and then a reflection about the x-axis, you could combine those into thinking of it as some rotation about some axis that's pointing, or some line that's pointing through the origin. I can try to even visualize it right now. It would be the midpoint between the two. So if this is V, this is something like BA acting on V. Then we could imagine like that there's a line passing through them, this dashed line right here. And the act of performing B and A together would be reflecting it about that axis. Elements in this left coset, that is what they are doing, and that is the second part of the lemma. I hope by visually trying to describe that, at least as best as I can, that makes sense. And I think the main takeaway, what I'd like you to take away, is that SO2 is the group of all rotations in two-dimensional space. And then you can generalize that to n, in n dimensions. O2 is the group of all rotations and all reflections in two-dimensional space. And you can imagine generalizing that to a higher number of dimensions. But still, regardless of which group you're working with, you're seeing that there are these very intuitive ways of visualizing the transformations that are occurring for each of the matrix elements in this group. And you can imagine, whenever you want to rotate anything or reflect anything, what you are inherently doing is you're pulling a matrix, picking out an element from the orthogonal group. Hopefully that makes sense. But yeah, that's going to cover it for the orthogonal group. In the next video, what we're going to do is I guess kind of like a little bit of a teaser going into the next one. The orthogonal group, we restricted to only having real valued elements. The next group that we're going to look at is going to say, well, what happens if the elements are not necessarily real? What if we draw them from C rather than from R? Okay. But I have to wait until next time for that. But yeah, thanks so much for watching, and I will see you guys in the next one.